Okay, so this is our lesson 2.8.2 on rotational dynamics. So this will be a two-part lesson. This would be part A, and we're going to look at Newton's second law for rotational motion. And I'm going to add, we're also going to be looking at torque. Okay, so students, excuse my spelling, will understand how torque, or understand what torque is, and how it works in a system. Okay, so Newton's law is actually going to be in part B. This is part A. All right, so beginning, we have a bell ringer question. Okay, so this would be question 2 for this unit. Satellite is often thought of being a projectile which is orbiting the Earth, but how can a projectile orbit the Earth? Because previously we were like projectiles fell down, right? So doesn't the projectile accelerate towards the Earth under gravity? And as such, wouldn't any projectile ultimately fall towards the Earth and collide with the Earth, ceasing orbit? Okay, so we've discussed this a little bit before, and Newton had a theory where if he launched a cannonball with a fast enough speed that it would orbit the Earth. And that is essentially what we do with our satellites. They are in a constant state of free fall. They do not fall to hit the Earth due to their horizontal velocity. Okay, and we learned our equations for horizontal velocity. We could calculate how fast a satellite is going if we're given the period and radius from the Earth, stuff like that. Okay, so make sure you answer that question in Google Classroom. And again, we're looking at rotational dynamics 2.8. So this would be Unit 2. This is the way I code these. Unit 2, or Module 8, Lesson 2. So if you wanted to read the textbook about this, this would be Module 8 and Lesson 2. It's titled Rotational Dynamics. Okay, so check that out in the textbook if you would like to. All right, so let's get rolling. So I can come back to these if I need to. This will be a review from 2.8.1 when we just looked at angular velocity and angular acceleration and angular displacement. Okay, so the question here is, how does force affect rotation? So if I apply a force to something, how can that affect my rotation? We talked briefly about circular motion and how that begins, and we can swing something from a rope or a chain. That'll be a centripetal force. What if I am pushing something and it turns at an angle? Okay, so an example here, we use a door. Okay, so a pretty good example for torque here. I got my door, hinges are here, so this part right here would be called the axis of rotation. Alright, so axis here, oops, and our axis here for that one. Okay, so just where the hinges are, that would be considered the axis of rotation. Now this diagram here is like I'm pulling on the door really close to the hinges. Okay, so I'm thinking about pulling on that door really close to the hinges. Alright, and then this one here, I'm a little bit further away. So let's say we're pulling from the center of the door. Okay, so that's going to give me a little bit. That'll work on the door, but the best way, and this is the way the doors are engineered this way, it seems kind of silly, best way would be out here, pulling on the edge of the door, because that's going to give us the most pull on it, which is called torque. Okay, so a couple other things, a couple other examples we can look at. Okay, so we have right there. So pretend you are grabbing a door and you're like pulling on the doorknob towards yourself, kind of from the edge there. So you're pulling straight out from the door. We could maybe say that that is 180 degrees or 0 degrees or something like that. Okay, so that's not really going to do anything. And then right here, this one is kind of pulling. It's not pulling straight on the doorknob. I'm kind of standing off to the side and I'm pulling at an angle. Okay, so that one's not going to do as much either. The best way to do it is pull straight from that. Okay, so it seems kind of silly that I'm talking about this stuff, but that introduces what is called torque. Okay, so and torque can generate an angular velocity and an angular acceleration. All right, so essentially torque is just an angular force. Okay, so we're applying a torque or an angular force to something. Okay, so here's some things to look at. So the change in angular velocity depends on magnitude of the force, distance from the axis to where the point, or distance from the axis to the point of where the force is exerted, and direction of the force. Okay, so these things, again, they're talking about what is called torque. Okay, so this one would be how much we're pulling or how much force we're pulling, how far we are from the axis of rotation, because that makes a difference, right? You're not going to try to open a door right next to the hinges, and then the direction of the force. So this talks about the angle, and you're not going to try to pull the doorknob towards you if you're standing on the outside edge of the door. That'd be kind of silly. It's not going to do anything. Okay? So when we're talking about force and angular velocity and torque, we have this thing called the lever arm. All right, so we have to consider that. Okay, so if we're given applied force, depends on our lever arm, which is usually perpendicular, which is the perpendicular distance from the axis of rotation. Okay, so this is back to our door axis of rotation there, and generally the lever arm is going to be perpendicular to that axis of rotation, right? And so depending on our size, so this arrow right there is talking about the size of our lever arm. If we had a door that was 4 feet wide with the handles at the edge compared to a door that was 2 feet wide, say if we cut this in half and put a doorknob here, it's going to be a little bit harder to open that door than if we have the longer lever arm and the handles out here. Okay, so the lever arm, that affects the amount of force or the amount of torque, really. Okay, so a lot of times, so here's some just kind of general information, but a lot of the time torque is talked about in mechanics. So we have a crescent wrench here, and it has all this wonderful math next to it. Okay, so this is talking about our equation for torque. Okay, so if the force is perpendicular to the radius of rotation, lever arm is the distance from the axis of rotation. So wherever I put my hand on this wrench, which is usually, depending on where the bolt is, usually here or here, that is going to be your lever arm from the other end. So let's say our bolt is here, and we have our hand down here. So the lever arm would be the length of that wrench. Okay, so then the next bullet here, if a force is not exerted perpendicular to the radius, the lever arm is reduced. So what that is talking about is this part right here, that theta. Okay, if I have an angle, so this one, for example, I'm pushing on this crescent wrench with this angle. Now, we know the best way to do it would be like that, right? So whatever this angle is from here to here, that's going to reduce the amount of force that I'm pushing at. Okay? So then your lever arm, so once you have an angle, lever arm can be r sine theta. Okay, so that's just a little trigonometry. We got it right there. If we want to figure out what our force is going to be, right, we could draw a right triangle, figure out, or use this to figure out this component, which is essentially that force right here. So you're trying to find that perpendicular component, which I'll give you guys. This will be a little formula that makes it pretty easy. Okay? So that angle, if you're pushing at an angle or pulling at an angle, is kind of important for calculating torque. Okay? So, I've said this quite a few times already, the word torque. So, it's a measure of how effectively a force causes rotation and is the Greek letter tau. So, sometimes when I'm here writing this, you're going to see me draw like a squiggly T. It's not going to be straight. Sometimes it'll kind of, I can get it right on my tablet here. So it'll be kind of like that, like a little hook on the end there, or something like that. Okay, so, and I will say, hey, this is torque, people, and we're going to write the equation for it. All right, so this is a torque wrench. That's usually the most common example because sometimes you have to torque bolts or torque spark plugs to spec or torque the lug nuts and stuff like that. So it's kind of a big deal. It's in mechanics all over the place. Okay, so here is our equation for torque. So the magnitude of torque is the product of the force and the lever arm. So this one here is the most basic equation. That's just, this would be if I push on something at a 90-degree angle perpendicular to that lever arm. So whatever the force is times whatever that lever arm is. Now the second equation here, put a little asterisk by this because this is important when we have that angle. Okay? Because remember that angle is going to essentially reduce our force, or I guess reduce our lever arm. Well, it's going to reduce the overall torque, but it'll reduce that force. Okay, because we're pushing on something at an angle, and it's going to take it down a little bit. Okay, so we have labels for torque. So because force is measured in newtons, that would be this guy right here. And distance is measured in meters, so that would be this guy right here. Angle, you can just usually use whatever the degrees there are, or they are. If you have a radian measurement, which we probably won't give it to you, but you'd want to convert that to degrees. So remember your conversion, 1 radian equals 57.3 degrees. Okay, you might need to use that. That's the quick conversion for radians to degrees. Okay, another one, so this is metric. Right here, this is our SI. The English, that would be foot-pounds, and you write it like this. Okay, pound-feet. I know it looks goofy, but it's foot-pounds because our force in the English measurements would be pounds, and our measurement, the American standard, or American, is feet and inches, so we go by feet. Okay, so make sure you write down what these variables are. Okay, so that's torque, that's force, that's radius from the axis of rotation, which is essentially our lever arm, and that is the angle that we're pushing at. Alrighty. So I've talked about this a little bit. You can kind of read through this while I'm talking. But it's torque. We use torque for crescent wrenches and stuff like that. We're also use that for gears. So this would be maybe like a starter on a car, and then this would be the flywheel. Okay, so it's quite a bit bigger than that actually, but that's kind of the idea. So our starter has to produce the correct amount of force on the flywheel to turn the flywheel and get the pistons rolling there to start our engine. Okay, so here's something that kind of comes into play a little bit. Lesson 3 is going to talk more about equilibrium. Okay, so read this here. Clockwise and counterclockwise torques cancel each other out. So when these torques cancel each other out, then the object or the system is in equilibrium, and it doesn't actually rotate then. Okay, so if opposing torques don't cancel each other out, then the net torque is going to cause a change in the rotational speed. So that is what could actually cause our angular velocity or angular acceleration. So, basic example, right there. We have a couple people just sitting on a seesaw, and we will say that this system here is in equilibrium. Okay, so if I took this person off, obviously the seesaw is going to go down this way, right? But it's not going to go straight down because it has an axis of rotation there, so it's actually going to go on a rotational axis, right? That would be our rotational motion. Now, let's take this person and let's put them back on there. Let's get rid of that x. Okay, so technically we have a torque from this person going that way, and we have a torque from that person going that way. Okay, so these are opposing torques, Okay, because this one would result in a clockwise motion, and this one would result in a counterclockwise motion. So they're opposing torques, thus the system is in equilibrium. Okay, and we will work on calculating torque here in a second. So here is just, if you pause the video and read through this, this would be something where torque is important. We have to know the correct amount of torque so we do not strip bolt, or we don't strip the screws, we don't strip the bolts, we don't break the bolts. Okay, it's important for engines and motors and stuff like that. All right, here's another one. So here's something to kind of think about. You're defending the goal line and the last defender to tackle the other player. You hit the other player within 1 to 2 yards of the goal line. How should the player be tackled in order to prevent the player from being carried over the goal line? So let's see how well I can draw my football players here. All right, so this is the guy carrying the ball going that way. We got our defender. Okay, let's give him some pads here. All right, and then we have our goal line there. So how am I going to tackle this dude so that he doesn't get over that line? Okay, well, it's pretty, you can kind of, if you know football, it's pretty obvious. If I'm trying to get the guy from going to the goal line, I am not going to tackle him down there. Now, that's a pretty effective way to get somebody down. However, what is going to happen when you tackle him down there? He's going to go like this, reach out, put the ball in the end zone, and touchdown. Okay, so do we want to hit him right there? Do we want to tackle him right there? Well, depending on how big he is and how fast you're going, that could result in a stalemate, or that could result in you going back or him going back a little bit. But let's just say that he's going faster than you. All right. So what you're going to want to do to prevent him from going in there, you're not going to take his head off, but we're going to tackle him in the upper half of the body, because what is that going to do here? If I hit him in the top half of the body, that's going to create a rotational motion going back that way, and you've essentially prevented him from getting in the end zone. So obviously the rules, you can't tackle a dude by the face, but you'd want to hit him in the upper half of the body to create that torque to make him fall back. Okay, so that's torque in action for you. So let's practice a quick example problem here. So we got a torque wrench, lever arm of 1.5 feet. A force of 40 pounds is applied at the end of the wrench to tighten the bolt. What is the torque in pound-feet? So our bolt or nut, whatever, was going to be right there, because this would be the end of the torque wrench. I showed some of you in class what a torque wrench looks like if you've never seen one before. But you always go from axis of rotation to where I am applying force, which would be right here. So it's a pretty simple equation. First, we are pushing on our torque wrench straight down. Okay, so that would be perpendicular or a 90-degree angle if you wanted to use that FR sine theta one. Okay, so let's write our equation out. Torque equals force times radius times sine of whatever angle. And since you're pushing at a 90, we don't need that, right? So I said this is our basic equation. So it's just going to be force times radius, or force times lever arm. Okay, so our force that we're applying is 40 pounds, and our radius of rotation, 1.5 feet. It's pretty simple, just multiply those two together. Okay, so 40 times 1.5, and you will get 60. Okay, so again, our label here is going to be pound-feet, or pounds, however you want to say it, for this one, because we are using English measurements here. Okay, so pretty quick. So here, this one's a little bit more advanced. So we have a seesaw problem. Oops. See if we can get this to cooperate for me. Okay, so we got a seesaw torque problem. We have person A and person B sitting on the seesaw. And person B weighs 500 newtons while person A weighs 1,000 newtons. The distance of person A from the center is 1 meter. So this is person A, his distance is 1 meter. How far is person B from the center? So we don't know how far this dude is from the center. Now, you could probably do some quick common sense thinking here and say, well, this guy weighs 1,000 newtons. He's 1 meter. That guy weighs 500 newtons. So he's probably going to be, since he's half as much, he's going to be twice as far. Well, yeah, it's not always that simple because we could have two things. Maybe he has a dog or something sitting on the seesaw. So we are going to show how this is in equilibrium with a little bit of torque. Okay, so this one, we're going to assume that it's an equilibrium. It's not going down because it's not showing us going down. So we're going to find the torque of person A, and equilibrium means that they are equal. So find the torque of person B. We're going to set those two equal to each other. All right, so torque is force times radius. Okay, or force times lever arm. We'll say this is person A, this is person B, so that way we can kind of keep it straight. And we have our radius of person A, radius of person B. So let's start filling in the information. Person A, his force is 1,000 newtons. Okay, and we're given his radius is 1 meter. So person B, his force is 500 newtons. And his radius is, we don't know. So we are going to not mark that question mark. We're going to leave that as an R for radius of person A. Okay, so a little bit of quick algebra here. 1,000 times 1, that's 1,000 over here. And it's Newton meters. And then over here, we've got 500 newtons still times the radius of person A. We got to get rid of that 500. So divide it out. And just as we suspected, I'll write my newtons in there. Just as we suspected here, it's going to be 2 meters. Okay, so the radius person, not A, that's radius of person B. Okay, that should be B, not A. But we get the general idea here. All right, person B down there. Okay, so he's 2 meters. So that makes sense, right? So that's how those problems work. The big thing here is recognizing if we have something that's in equilibrium, or if you're told that it's an equilibrium, you set the torque of the left or right, whatever. So we went torque of A, which is that guy, and set it equal to torque of B, which is that guy. Okay, so there's a simulation coming up that I'll have you guys look at and do those. Okay, so we're looking at some practice problems here with torque now. Some of these might be a little bit wordier, so you might want to read them a couple times before you get started. Okay, so you'll have some assigned to you from the book, from the reading, or I may have a worksheet that you can do for practice problems. I might also be able to look for some on Khan Academy, but we will see. Okay. At what point between the hinge side and outside edge of a door would a given force perpendicular to the door produce the same torque as a force of equal strength but at a 30-degree angle along the outer edge of the door? So we know, so force 1 is going to be equal to force 2. So our forces are equal. We're trying to figure out how far along the outside or how far along a door, not really terribly drawn door. We're trying to figure out how far from my hinges would I push 90 and then push 30. Okay, so I'm probably going to have to push, if I want to try to get my forces equal, so if I'm pushing at a 30-degree angle, I probably have to be closer to the outside edge because that 30-degree angle is going to reduce my force. Okay, so let's just say, for simplicity's sake, let's say our forces are going to be 1 Newton. Okay. So let's start off. Our normal equation for torque is force times radius or lever arm times sine theta. So let's say our first one we're starting out with. Our torque is going to just be at a 90-degree angle, so we have our force of 1 Newton times that lever arm, that radius. Okay. And I don't know, we could probably give that one an arbitrary number as well, because we're trying to figure out how far the 30-degree would be equal to the 90-degree one. So let's just say that one is 1 meter. Okay, so that means we have a torque of 1 Newton meter. Okay, so our general torque is going to be a meter out, and then now we need to figure out what would be the same if we had a 30-degree angle. So now we're going to use torque equals force times lever arm times sine theta. And let's use our torque from the last one because we're trying to figure out how far out our torque would be, or how far out our radius would be, sorry, to get the same torque. And we have 1 Newton. Okay, and then we're trying to find R, and then we have a 30-degree angle. Okay, so let's do a little bit of calculator action here. So we got 1 Newton times sine 30, which is just going to be sine 30, whatever it is. So it is 0.5 times my radius. Okay, so we're going to have to divide by 0.5 on both sides, which is going to give us 2. So that would be 2 meters for this one. So let's compare the two. Our original torque was 1 meter. We're pushing at a 30-degree angle, and we have to be out at 2 meters. So my answer would be R is going to be 2 times the length of the original. So I'd have to push at a force twice the original if I were, or push twice as far from the axis of rotation if I were using that 30-degree angle. Okay, so this is a little involved here, but make sure you read the question. And a nice thing, kind of a little trick here, if you know things are equal, like here the forces were equal, we could just set it as some arbitrary number like 1, or you could use 20, you could use 30, whatever. But for simplicity's sake, we just used a 1. All right. So if you know things are equal and you're trying to find stuff, find numbers, then just put a number in there like 1, and you can use that. Oops. Okay, so the second one here. A bolt on a car engine must be tightened with a torque of 35 Newton meters. Use a 25 centimeter long wrench and pull on the end of the wrench at an angle of 60 degrees to the handle of the wrench. How long is the lever arm, and how much force must you exert? Okay, so let's write some things that we know. So we have our torque is 35 Newton meters. Our lever arm is going to be 25 centimeters long, and we have an angle of 60 degrees. So your hand is at an angle of 60 degrees to the wrench. So let's say wrench here. Okay, bolt there. Hand is going to be kind of like this. And we got 60 degrees to that wrench. Okay, so now you might be thinking like, oh, well, okay, I'm going to have to use 120 degrees to get 180. No, we're just going to use the 60 because that 60-degree angle here is what is reducing my lever arm. Okay, so this one's pretty simple. We're just going to use that 60, and we're looking for, it says how long is the lever arm and how much force must you exert? Well, our lever arm is just that, okay? So it's 25 centimeters long. However, remember our units are newtons and meters, so we don't want to use centimeters. We're going to have to change that to meters. So divide by 100 and you get a quarter of a meter, or 0.25. So let's solve this one. Fr sine theta. So my torque is 35 Newton meters. And our force, we don't know, so we're looking to find. All right, so we can write that over here if we wanted to. Come on, tablet. Force is question mark. Okay, so radius 0.25 meters. And then we have sine of 60 degrees. Okay, so let's do a little bit of calculation here. I'm just going to multiply 0.25 and 60 to write it down for you. Or 0.25 sine 60. And we have 0.2165 times my force. Okay, so I'm actually going to use that number that's stored in my calculator. A little algebra here says we just divide by 0.2165. And we have meters, so this should be meters oops, meters, so it'll cancel there and there. And then we do that in our calculator. So 35 divided by second answer, so we get that. And I have a force of 161.66. And what are my labels here for the force? That is newtons. Okay, so let's check out, oops, sorry about that. Let's check out the last one here. So what force is applied when the wrench from example problem 1 is used with a 35 Newton torque applied at an angle of 75 degrees from the perpendicular? Okay, so example problem 1, that guy, so we're using that same torque or that same wrench. Okay, so let's write that radius or lever arm 25 centimeters or 0.25 meters. Says what force, so we're looking for a force again, and we have a torque of 35 Newton meters. Okay, and our angle 75 degrees. So we're doing the same thing as we did in the last problem, we're just looking for that force. Okay, so we have a torque equals F R sine theta. Torque's 35 Newton meters. Force, we don't know. Radius, again, 0.25 meters. And then our angle now is 75 degrees. So we're just saying we want to make this even harder on ourselves by doing an angle of 75 degrees. So you could put all that in your calculator again. I'll probably do it all at once here. So those will cancel out. So divided by 0.25 meters and sine 75. So boom, 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 boom. What do we get? So 35 divided by 0.25 sine 75 degrees. And we get 144. Oh, okay, so I'm going to retract my statement of making it harder on myself. We want to get closer to a 90-degree angle, right? Because that 90, that perpendicular, is the best. So this one, if we compare our answers here, I'll show you why I'm taking back what I said here. I compare my answers here, so I had a 60-degree angle there at 161.66 newtons. Now I got a 75-degree angle at 144. So I was like, oh, bigger number equals more force. Well, that's not true because we want to get closer to 90, right? A 90-degree angle is the best for torque. Okay, so my bad on that, but we fixed that. So 75-degree angle would reduce my force. Okay, so hopefully that helps with our torque problems. Those three, you can kind of play those back again if you want to. These are going to be generally the equations you get for torque. Let's something that's this long, applying this much force at an angle, find the torque. Okay, so to finish up the lesson here, I just want you guys to kind of play around with this simulation here. Okay, so this is called the balancing system using torque. So there's a Colorado University, I don't know what the PHET stands for, it's just FET Simulation Balancing Act. I will show you guys how to get to that in a minute here. Okay, but that'll be kind of part of an exploration deal. But we want to do these book problems. Okay, so by the assigned due date in Google Classroom, we want to have those book problems done. And you can ask questions on them if you need to via email or in Google Classroom if you need to. Okay, so that's what we want to give a shot. Some of them, like most of them, are all torque problems, but you have some kind of a system in place sometimes. Something I didn't mention here, if I have two gears like this, a big gear and a little gear, the torque will be different on these two because we have a different radius. But if one of them applies a force to the other one, the force is the same between those two. Okay, torques will be different, but the forces will be the same. So that could also be, I think there might, if I remember correctly, there might be a problem with a pulley and then a basket on this side, and then a basket on this side, whatever their weights are. So it's like which one is going to apply torque to the pulley. That's kind of like the seesaw problems. So I figure out the torque by this one, or whatever that is. So that if I'm using a pulley, then it's usually that radius right there. So that would be my radius, or my R, and this would be my force down. So that's mass times gravity. Okay, so that one has a certain weight pulling down. This one has a certain weight pulling down. Find the torque caused in the system. So I would subtract my weights here, see which one's going to be pulling down. Obviously the bigger one's going to be pulling down. All right, subtract the torques and find a net torque. Okay, so those might be the problems that you're looking at. Okay, so let's go to this PhET simulation thing here. All right, so let's go to my internet browser, and I'm going to drag a screen over here. So I'll have the link for you, but you can type in PHET balance, and you will get balancing act. That is what you want. You're looking for that one, and this will be the screen that you get. Okay, and then we can click on this. And then we get to the screen. It says loading. Sometimes since this is the first time for you guys doing it, it might not load for you. It might have something that says allow flash player or something like that. So then you'll need to go to your little lock up here. And like this one, it says ask. So like you'd go to the flash player thing, or there might be something where you can go to here, like site setting, and then that'll open up a whole list of things for you to look at. So for that one, this has by default block the camera, but I would scroll down to where I see flash, turn on to allow, and then I can do the simulation. Okay, I'll give you guys a little worksheet. I'm not going to make it do. It's normally do, but I'm not going to make it do for you guys since it's in the e-learning situation. If we were not e-learning, then this would be do. But you can play around here. So just a kind of quick intro to this. I got nothing on here, so this is going to be balanced. This little button takes everything, takes my little pillars away. So the worksheet tells you to start playing around with things to figure out where you would put objects. Okay, so I got a 10 kilogram trash can. I got a 5 kilogram fire extinguisher. Now if I take this away, which way is going to be by net torque? That's going to be over here, because it's going to fall because there's more weight or more torque on this side. There's more rotational force. Okay, so let's put that back. So it says, well, if I want to balance it, well, I could put marks down there, right? So I'm 6 spots away, or I could do meters if I wanted to. So this is 1.5 meters away. Well, that's twice the weight as the other one. So what's half of 1.5? That's 0.75, right? So let's see. Hey, that's right. So I balanced it out. So I have essentially a 7.5. Well, I guess we have to take mass times gravity, but let's forget about gravity now. I'd have to take a 10 times 0.75, which would be 7.5 Newton meters of torque. And then this would be 5 times 1.5, which would again produce 7.5 Newton meters of torque. Now, if I wanted to put both of these on there, then I know that that's not going to work out. Okay, but I'm going to have to find the torque caused by these two, set it equal to a torque caused by this one, and find my lever arm. So I would figure out that, hey, if I put that at 1.25, that's going to be back to balanced. Okay, so this is just your intro to play around with it, and you can see the force vectors there. So that'd just be kind of showing me what level is. If I want to clear the board off, I go there. So the activity, the worksheet that I'll give you guys to kind of play around with it. The best part of it is, so if you go to Balance Lab or Game, you can kind of play around with this. So it's a torque game, so I can figure out where to put objects, and it's kind of like a mobile game where I get, hey, I did great, 1 try, 6 stars, or 2 seconds, or something like that. In here, we have bricks. Let's turn everything on. Forces from objects. We can see where level is. Ruler. Let's just go with the ruler. I like that better. So here you got different objects. So here I could put a 20 kilogram brick on there, 5 kilogram brick. I could put people on there. Okay, and then this is kind of the fun part, trying to find how much a mystery object weighs. Okay, we don't know how much these weigh. Okay, generally it'd probably be best to put them at 1 and then see how that pulls down. And now we're going to go back this way and we're going to start playing with bricks maybe. So let's put 20 kilograms of bricks at 2 meters. That's way too much. Let's put it at 1 meter. And boom. So that package right there weighs 20 kilograms because I have a balanced system. Okay, so that was actually fairly simple. Let's clear it off. See if I can find a harder one. Let's do B. And let's put our marks on there, our ruler on there again. So that's pulling down 1 meter. It's not as fast now. Okay, so it's not pulling down as much. So that tells me it's lighter, right? So maybe I need to put something here. Let's go back to our bricks. Let's maybe try 10. And so, boom, that was a pretty good guess. So that one's 10 kilograms. So I did a couple of them for you. There are 8 packages. So if you want to give it a shot, it's on that worksheet, but I will provide that to you guys and answer questions that you guys have on stuff. Okay, so hopefully this video was helpful. Let me know if you got any questions. Good luck.